All right, next up we have one of my favorite topics in chemistry, and that is thermodynamics, because this is going to be what tells us whether or not a reaction occurs. In Chem 1, we may have looked at some thermochemistry, we've looked at the enthalpy change of a reaction, but as what we're going to learn here, there's much more than just enthalpy or thermal energy that has to do with whether or not a reaction will or will not occur. And we'll see that sometimes it's the conditions that are surrounding the temperature that determines whether or not a reaction will or will not occur. As we're looking at thermodynamics, we're going to be learning about a new state function called entropy, or the measure of disorder, that is really critical to understanding thermodynamics, but also further topics in chemistry and physics moving forward, and is really, quite an interesting philosophical conversation starter as well, in my opinion, and I hope yours too. So with that, we'll go ahead and jump into thermodynamics. The first thing we need to consider when learning about thermodynamics is this idea of spontaneity, because thermodynamics is so closely related to whether a reaction or process is going to occur or not. And this is the idea of a spontaneous change. So this is a classic thermodynamic example where we have two volumes of gas that are separated by a divider, a stopcock here, which we can open up and basically remove. And so if we have the two chambers where the gas is all in one side and we're then to open the dividing stopcock, well, I think it does make sense that the gas is going to flow from one side to the other. That's the spontaneous direction. Thinking about it in the opposite direction, which is to say, well, we have this volume with an open gate, will the gas just jump back into one side and have one side have all the gas and the other be a vacuum? And the answer is no, this would never happen. That would be the non-spontaneous direction here. And so this is a great place to start, where this is a phenomenon that we know is going to occur. We know it's going to be spontaneous. And the reverse process is going to be non-spontaneous. So when we consider these reactions, or even just processes like this, there's no chemical reaction here. If it is spontaneous in one direction, it's going to be non-spontaneous in the other. Okay, another thing we want to review is this idea of enthalpy. So this should be something that you're a little bit familiar with at least already, or have heard it before, where we have this function called enthalpy, for which if a reaction releases heat, we say that it's exothermic, and that therefore it has a negative enthalpy, delta H less than 0. Again, we call this exothermic, and it means that heat is released and the enthalpy of the system decreases as it goes from reactants to products, because heat is being released. Heat is formed, so that heat must have come from that loss of enthalpy. Conversely, we have delta H greater than 0. We say that this is endothermic and heat is absorbed. But as we think about this is not the whole story over whether a reaction will or will not be spontaneous, because do exothermics always occur? And the answer is no, right? And are endothermic reactions always non-spontaneous? And the answer there is no as well. A good question here is about boiling water. Is it endothermic or exothermic? And as a follow-up, under what conditions does this actually occur? So I would recommend you actually pause here and think about this a little bit, right? Boiling water, endothermic or exothermic, and when does it occur? All right, hopefully you've gotten to think about this just a little bit. Is it endo or exothermic? The answer is that it's endothermic. It takes heat. We have to put heat into the water to get it to boil. And this is only going to happen at high temperatures, because at high temperatures, it actually does occur spontaneously. It will draw in heat from its surroundings and the water will boil. I think that, when we boil water most often, what we have is like a heat source that's boiling the water when the surroundings are lower. But a better way to think about this is, what if we take like a small sample of water and put it into, the middle of a volcano, something really, really hot? Well, it would draw energy in just by virtue of it being in a high temperature surrounding, and it would boil, and it would be endothermic. What is driving this change, right? Because endothermic, exothermic, generally speaking, exothermic is favorable and endothermic is generally unfavorable. But we just saw an example where that wasn't completely tied to spontaneity. And so what's going on is this idea of disorder or entropy, where when we have endothermic spontaneous reactions, they're driven not by the fact that they're releasing thermal energy, but they're driven by the fact that they're increasing the disorder or the freedom of motion of the system, which we're going to call the entropy. And this desire to become more disordered is reflected in many common phenomena, such as a deck of cards. There are many, many ways for that deck to be out of order, but there's only one way for them to be all lined up. And a further example is, if you were to take a deck of cards and just sort of leave it without a rubber band around it or anything in the middle of the floor or on a table, and over time, it would probably just become messed up. Someone would play with it, it would get knocked over, who knows. Disorder is how the universe tends to progress, and this is reflected in chemical reactions as well. Another great example is, a bunch of wires, a bunch of electronics. This is a bit of an outdated pile of electronics, but hopefully this idea of wires tangling together is something that you may recall. And keeping them all straight does take a constant input of energy. And if we just let them do their own thing, we'll see a mess as shown here. So what is entropy though, right? Because qualitatively, I think we can see some of the parallels in general phenomenon that things tend to get more disordered. Entropy, more specifically, is a physical property that is characterizing this amount of disorder. How much randomness or disorder is this system? Because when that disorder is increased, the energy of the system is actually more spread out, and that is a more favorable spot to be in. The energy doesn't like to be well organized within a system. It likes to distribute itself, and this is shown in an increased amount of chaos and an increased amount of entropy. So I would recommend you go ahead and pause the video here and try this activity. Consider a few spontaneous phenomena that demonstrate that the universe favors disorder. And if possible, think of some chemical reactions when you're thinking about whether these are entropically favorable, or rather how they can be shown as entropically favorable. All right, hopefully this is a good little chance to stop and think about entropy. Some things that I like to think about, are the examples that I showed previously. But I think, anything that is getting more disordered over time, more jumbled up, is great to show that the universe favors disorder. And from a chemical standpoint, this idea of water boiling, we said that it was endothermic, and so that must mean that it's driven by a positive entropy change if it's going to happen spontaneously. This is to say that the gas state is more disordered than the liquid state, and that kind of makes sense as well, because the liquid state is contained to a specific volume, whereas the gas state is much more free to fill whatever container it's in. Other reactions like burning gasoline, we may have just like one gasoline particle, one larger hydrocarbon, and when that's burned, it's actually going to become a bunch of smaller gas particles. That's a much more disordered state than when all of those bonds are concentrated in a single molecule. Okay, so what else would we want to know about entropy qualitatively? We could do a whole course on entropy and spontaneity, so really this is just the broad strokes here. First of all, it increases with temperature. This on the left may be a graph that you've seen before, where temperature is the average kinetic energy of a system. And if we have a higher temperature, we're increasing the average kinetic energy, but we're not increasing the kinetic energy of all molecules or particles. We're increasing the average, and so it's this distribution that gets shifted over, where still there are some that are moving very slow and some that are actually moving quite a bit faster. As we increase our state, our physical state as well, solids have less entropy, liquids have a bit more, and gases have much more entropy than the others. And we see that as we're boiling or melting, while we're not increasing in temperature, we surely will be increasing the amount of entropy of this system. Again, solid, liquid, gas. Solids and liquids have effectively very similar volumes. These are the compressed states, and even if we go from solid to liquid, generally there's not a radical change in volume, but gases have access to so much more volume because they're going to fill whatever container they're placed in. So there really is no limit to the volume that a gas can access, and for this reason, they have much more entropy than others, and when we have the formation of gases from non-gases, that's usually indicative of large positive entropy changes in reactions. Okay, entropy though is not spontaneity, because we talked about enthalpy and we've talked about entropy, and together we say, well, this makes for whether it's spontaneous. And this is a very important formula. This is Gibbs free energy, which says that delta G, this is the spontaneity, a new function that tells us whether or not a reaction will occur, it's equal to the enthalpy change minus the temperature times the change in entropy. And so if we use this formula, then if delta G is less than 0, the free energy is going to decrease, and therefore it's going to be spontaneous. This is like the reaction wants to roll downhill. We're going to get to a lower position than we were at before and release energy. This shows spontaneity. And this is reflected in what we learned about heat being released as well, but now closely tied to whether or not it's going to occur, whether it's spontaneous or not. If it's greater than 0, then the free energy change of a reaction is increasing, and it's going to be non-spontaneous. Let's think about the conditions that we know to be favorable. So if it's exothermic and the disorder increases, we've decided that exothermic is more likely to be favorable, and that increasing disorder is also more likely to be favorable. Well, if we take a look at this formula, then delta G is always going to be negative because we have a negative delta H, right? Delta H less than 0. And from this, we're subtracting a positive value. So we're taking a negative value and we're making it more negative. And therefore, delta G is always going to be less than 0. And so in all cases, it's going to be favorable and it's going to be spontaneous. Exothermic, increasing disorder, always favorable. What about if we think of the conditions that are less favorable? Well, what if it's endothermic with the disorder decreasing, which is to say the delta S less than 0? Well, in this case, the delta H is going to be positive, and we're going to subtract a negative. So we're starting with something positive, and we're actually going to be adding to that because we're subtracting a negative number, which is like adding. One point here is that T, of course, is in Kelvin, and so it's always going to be positive, and so it's not going to change the sign of delta S. But in this case, delta G is always greater than 0, and so it's never going to be spontaneous. It's always non-spontaneous if we have these conditions where it's endothermic with the disorder decreasing. So these are the clear cases where both processes are aligned, right? Both are unfavorable or both are favorable. But what about the other two cases? What if we have one is favorable and the other is unfavorable? In this case, it'll be the temperature that determines the spontaneity, and so let's take a look at this chart. In red, we have our double non-spontaneous, or our double unfavorable, which makes an always non-spontaneous reaction. And in green, we have our double favorable, so it's always spontaneous. If we have the other cases, so in the bottom of this chart, we have delta H less than 0, that is exothermic, and delta S less than 0, which is getting more ordered, less disordered. In this case, it starts out as spontaneous, but at a certain temperature, right, as temperature rises, we see the free energy crosses over 0, and it goes from being spontaneous to non-spontaneous. So these are only going to be spontaneous at low temperatures. And likewise, if we have a process, this is the upper orange curve, where delta H is greater than 0, so that's endothermic, but delta S is also greater than 0, so that would be disorder increasing and endothermic. Then it's going to start out non-spontaneous, and it's going to become spontaneous. Another way to think about this is that imagine the temperature is 0. So if it's endothermic with temperature equals 0 Kelvin, so absolute 0, then delta G is going to be purely determined by delta H. Another way to think about it is if temperature is infinitely large, then only the entropy term will scale, and it'll effectively be equal to only negative T delta S. So entropic contributions scale with temperature, while enthalpic contributions don't. And that's another way to interpret this graph, which I think can be very helpful. The take home, though, is that when we have these competing factors between entropy and enthalpy, that there will be a temperature at which the behavior crosses over, going from non-spontaneous to spontaneous or spontaneous to non-spontaneous. And to wrap things up, this is a useful chart to consider. So we talked about the green and red cases where the delta G is either always going to be spontaneous or it's never going to be spontaneous. And if we have the two competing factors, then we have the process spontaneous at either high temperature for endothermic and increasing entropy, or at low temperature for exothermic and decreasing entropy. All right, so this is our first foray into thermodynamics. Again, we could discuss these factors at great length, the temperature dependencies of all of these, and many other factors, and there are whole fields of science dedicated to thermochemistry, thermodynamics. But for now, this idea of spontaneity, of this new function that we've called entropy, and the free energy function is what's good to focus on. And as you move forward here in general chemistry too, we're going to see this delta G dealt with quite a bit because, again, it determines whether a reaction will or will not occur, and therefore is very much related to other chemical phenomena. All right, I hope you enjoyed this video on thermodynamics, and I look forward to discussing more chemistry in the next one.